Train a language model only on short tasks, then test it on tasks 8 to 32 times longer. A standard transformer mostly learns the short training distribution. Put the same model inside a recursive language model harness, and the authors report roughly 10 times the evaluation lift for the same training lift. The central claim is that the harness, not just the neural network, can carry the structure needed to generalize. A harness is the program between an environment and the language model. It decides what part of the current state becomes a prompt, whether to split the work into several model calls, what tools or submodels to invoke, and how their outputs determine the next action. Claude Code and Codex are harnesses. This work argues that tool access is only the surface-level benefit. In a standard agent loop, the main context accumulates the task, reasoning, tool outputs, errors, and more reasoning. The prompt grows into a task-specific history, unlike the shorter, cleaner sequences used in training. That is one account of context rot. The proposed target is not to make this giant trajectory familiar. It is to make every individual model call familiar. The authors call that target locally in distribution. The overall job may be novel, enormous, or too long for one context window. But each model call should receive a small observation resembling something the model already learned to handle. Classify this chunk, extract these records, or combine these summaries. The full trajectory is unfamiliar. The local steps are not. The first mechanism is context offloading. Instead of pasting a 2 million token corpus into the root model's prompt, the harness stores it as a variable inside a code environment. The root model sees a handle named context and writes code that selects slices. Different corpora can therefore begin with nearly the same root prompt, because their task-specific tokens stay outside the main context. The second mechanism is programmatic subcalling. The root model can fan out small prompts, store every answer in variables, filter or aggregate them with code, and pass only selected information into later calls. Tool and submodel outputs do not have to flood the root context. The root sees the reusable algorithm, split, search, aggregate, while subcalls absorb the domain-specific details. This figure compares a browse-comp plus training problem with an oolong evaluation problem. Their surface tokens and answers are unrelated. Yet the root model can follow the same three-step trajectory. Propose a decomposition, fan out queries over chunks, then aggregate the stored results. In the author's loose terminology, the harness makes the two tasks isomorphic from the root model's point of view. That gives a useful way to think about generalization. Instead of learning a separate long trajectory for every dataset, the system learns an equivalence class. All tasks solved by chunk, search, and aggregate. All tasks solved by filter and count. All tasks solved by map and reduce. Learning one member can transfer to another when the harness preserves the shared decomposition. For length generalization, the authors train Qwen3 to 507 on short splits from 6 environments. Training runs for 150 reinforcement learning steps, with batch size 64 and 4 rollouts per sample. Evaluation uses the same task families but inputs or outputs 8 to 32 times longer. A base transformer with yarn is the direct training comparison. Across all 6 environments, the RLM improves on the long evaluation split, even though it trained only on short tasks. The base transformer's training reward often grows as much or more, but its long evaluation score stays mostly flat. On 4 tasks, MRCRV2, GraphWalks, Oolong, and Oolong pairs, the trained Qwen RLM approaches or exceeds the plotted GPT 5.5 RLM comparison point. The stronger test changes the domain itself. The model trains on one kind of aggregation, retrieval, or similarity problem, then evaluates on different content with the same latent strategy. Over 500 steps and 3 train-to-evaluation domain pairs, the RLM shows clear transfer. The base transformer mainly learns answer formatting and does not meaningfully improve on the new domain. The harness does not guarantee the right abstraction. On short tasks, the root model can take a shortcut, send the entire problem to one subcall. That solution fails when the input becomes huge. In MRCRV2, a small instruction to decompose helped the RLM discover the length-agnostic strategy. The open problem is how much supervision is needed to make generalizable decompositions emerge reliably. 4 similarly sized tasks, RLM training takes about 1.5 to 3 times longer than direct transformer training. Multiple steps, parallel calls, and stored intermediates all cost time and memory. The author's scaling argument is that long contexts make the direct alternative grow worse. Training one bloated trajectory can be more expensive than training many bounded local calls. But the comparison is not free. Locally in distribution is an intuition, not a quantity the experiments measure directly. The appendix compares train and evaluation trajectories using edit distance and n-gram overlap. Those proxies show that RLM trajectories look more similar, but they do not prove semantic equivalence or bound the model's output distribution. The results support the mechanism. The formal theory of harness-induced equivalence classes is still unfinished. The takeaway is not that every agent should hardcode MapReduce. It is that the program around a language model can carry a higher-level inductive bias, hide irrelevant detail, compose familiar operations, and keep each call inside a regime the model can handle. If this result scales, future model architecture will not end at the transformer boundary. The learned harness will be part of the architecture too.